Now it's open for questions.
Wonderful talk, Evelyn. Thank you for giving us such a wonderful tutorial. I always wonder if you were to create those defects that you want, you were doing it by ion bombardment. Is this something that is highly precise and controllable?
Stella, you ask a great question. And actually, I haven't dwelled on this because this is an introduction. But one of the things that is actually the most difficult part of this is to put that defect exactly where you want it, and actually to put one defect, not clusters of defects. So you're right, Stella. Ion bombardment seems really inelegant, a really bad way of doing it. So let me answer you as quickly as I can. People have tried to do patterning and masking, and then bombard either with ions or electrons. People have used specially designed focused ion beams to try and place ions in the right place. There are two issues. One is the residual damage, although we do annealing steps often. Two is that you know that you can do simulations, but ions don't go where you want them. They scatter. We tried to, and actually people have looked at this for diamonds as well. We thought maybe if we do an electron irradiation, the residual damage will be less. Turns out and maybe just because of our sensitivity, we don't see much difference between ion bombarded samples and electron bombarded samples. I will say unusually though, we have had some experience where even we ion bombard, we don't do an anneal, and actually the results are almost indicate you don't do an anneal. I will say one thing that we're working on. So, you know, this is the ongoing problem. People still worry about this with diamond, and they've had a lot more experience working with diamond. One thing that we're trying to do, and because we saw evidence of this in some of the data I'm not going to show you, is if you have a few let me use this. If you have actually a few defects in almost in the right position, and this volume is very small. We did this because actually we made measurements, we bombarded, we didn't implant, and we got very good results. But then we decided, okay, we implanted, we didn't anneal, we got pretty good results. So he said, let's just try annealing. So when we tried annealing, we saw something very interesting, which when you anneal, there is some healing of the resultant material, but there's some diffusion of the defects. And actually some of the defects, so some of the peak heights increased. And right now we're exploring, although it may be very difficult, is perhaps we can do something strategic by placing the defects almost in the right place, and then understanding the diffusion process enough to do some kind of diffusion to nudge it in the right place. And we're working with theorists. They're calculating the energies of formation, the critical diffusion times, and diffusion energies. Again, I think it may be a process that can work. We'll see. We'll see about the stability of the defects.
No, there's a question in the back from a student.
Thank you very much for the nice talk. I want to ask about, like you explained the concept of microwave field on the ground state. How about that if we put the same kind of strain on the excited state?
Same kind of
strain or same kind of microwave on the excited state?
You certainly could do that. It's a different frequency.
No, but what will happen? Like, how you predict that?
Well, here's the issue. Actually, I would ask you. Okay, let's take diamond. So we have, let's go back. Because this is actually a question you can answer. according as in the simplified way that I've presented this. So you're saying instead of mixing the states here, why don't we mix the states here?
Yeah.
I think you can guess, so I want you to think about it, okay? Here's the problem, right? Here's the problem is that if my initial population is ms plus or minus 1, and I excite to here. And from here, it's likely that I go through this non-radiative transition. But if I'm here, I can have photon emission, radiative transmission to the ground state. So what happens if I do microwave mixing here? I think you can think about it, reason it through.
So it might be like the coherence time will be increased.
Sorry?
The coherence time will be increased.
So the coherence time, actually, right now we're looking, the net coherence, we're looking at the electron residence time. We're not looking at the coherence time of the spin. So right here, when we're talking about the electron transitions, you're looking at to see the residence time of the electrons at any particular state. And you can look it up. I think there's a lot of information that exists there in terms of the typical residence times. But basically what you're talking about, here's the issue in the differences between the transitions. Here's the metastable state or shelving state, which prevents, which likely prevents our signature from here, getting an output in a photon signature. You talk about mixing these states up here. I think you can guess what might happen. So you should think about what might happen and then propose an experiment or see if an experiment has been done mixing here.
Okay. In case of, like, my second question is that in case of bulk phenomena, and we are probing the NV center with like 537 and 637 or 557 or 637, then how we can differentiate between the output of NV minus and NV zero?
Here,
Yeah.
it's a different photon energy.
So what kind of how we what is the natural difference between this NV zero and NV minus?
So what the difference is a charge. So it's the difference with a charge and a spin. So here's NV0. I can't easily show it actually exists in the solid state, and that's one of the issues. Actually, one of the issues is it looks clean. It looks like it's a nice carbon diamond framework, but there is residual charge, and that's what happens to the solid state. So the difference is the extra electron. So if you look at any spectrum, if you look at the molecular signature of something like, I'm making something up, He+, He++. Look at any, so if you add an electron, it changes all the electronic states. In this case, an additional electron pairs with an electron in the nitrogen region to get a net spin 1. It changes the entire energy structure. So you would have to look, if you don't have it at hand, the calculations, if you were to start from first principles and calculate the energy levels, it's a different set of inputs. Different electron, number of electrons, different charge, different, so, I mean, this is what's physically observed, but people have calculated. I believe people have calculated what's expected for NV0. So anytime you subtract a charge, two charges, the spectrum changes, as it should. Because you would like to believe that the information you get from a photon is something distinctive about the atomic molecular system.
Thank you.
There you go. Third row, right here.
Why the photon bouncing in the cavity instead of leaking out from the holes?
Good question. Is there a board?
I'm
Okay.
sorry, I don't think there's a board. Next time we should prepare a flip chart.
If I have a photon, so imagine in my hands is a box, and the box is a material where the index of refraction, I'm just going to make it up, is 3. Okay? I have a photon in this box, and the photon has some energy, so it's bouncing around. Tell me what happens to the photon.
I think it will go through the internal reflection.
Right. Okay, good. So now I put a hole in the box. Let's put a cylinder in the box. And I have that same photon. What happens to that photon? And is it 100% guaranteed that it will leak out through the hole?
No,
Why?
only some reach to the hole.
Some reach to the hole, but at the hole is the interface between index equals 3 and index equals 1. So here's, let's say my hand is one wall of that cylinder. So there's a cylinder, and the photon is bouncing around. Unless the photon hits that cylinder wall at the right angle, it's also going to be totally internally reflected.
Thank you.
Okay. So this is a very powerful device where you can tune the wavelengths to be detected. Is there a limit? I mean, so you can this range of wavelengths that you can.
You mean with the optical cavity?
Exactly, right.
Oh, yeah. Yes. The fact is there's always a limit because imagine you make this beautiful, I don't know what actually what musicians do. If you play a wind instrument, I don't think you do this, but sometimes you try and influence the tone of your instrument, maybe by doing essentially something like you clamp something onto the material, you change the geometry, you change the structure, you get a different tone. You know you can't do that forever. Same thing is if I have this bridge and I keep placing monolayers of gas and I shift the frequency to longer and longer wavelengths. Well, at some point, I put enough of this material onto the surface, and then I have to think about the optical interface, the fact that putting this material on, so we make these elaborate models under various assumptions. And see, when I look at this, actually look at this is side view. So here's where the electromagnetic field is, but you see the electromagnetic field, here's the outlines of the bar. This electromagnetic field is not tightly within the silicon carbide. It's beginning to sort of spread out. That's called an evanescent wave. It means that that's leaky. So this mode here is a little bit leaky because you can see a little bit of the field. So now I keep piling stuff on top. I change the optical properties. So to some extent, if I just put monolayers, I can think of this as my instrument and I'm just tuning it slightly. I put a lot of monolayers on. I think I can put 50 monolayers and tune it all the way. What I've done is change the optical properties and actually have changed the leakiness. So there is a limit.
So at this point, I'd like to thank Professor Hu for coming here to give us an inspiring lecture.